Holy heck, it's May. Hey kids, it is May 1st, it is Friday, and on today's edition of Kitchen Table Chemistry, we're going to take a look at equilibrium concentrations and a technique called approximation. So what this is as follows. Approximation, we understand what the word means. It allows an equilibrium question to be solved more quickly and to avoid the quadratic equation. This is desirable and lets us just move much, much more quickly and get approximately the same answer. It's based on the idea that if K, the equilibrium constant, is really small and the amount of reactant is really large, then the amount of reactant lost is not significant to the answer. So here's the idea. If the amount of the concentration, so the concentration, the amount that we start with, divided by K is less than 1,000, we can't approximate it. It doesn't work. So here, if we have an initial molarity of 0.5 and a K here, if we divide these, if the value we get is less than 1,000, then you can't approximate, and you're going to have to figure some way out of it. So if I was to take that 0.5 concentration and divided by 0.0042, I would get an answer of 119. That is not going to allow me to approximate. It doesn't work. Can't. Concentration divided by K, if it's greater than 1,000, then approximation works. It really means that we're losing so little of this reactant that it's not going to be significant to the final answer. So if I take this 0.5 concentration, and now my K is much smaller. My K is 4.2 times 10 to the negative 5. This means that most of the reactant remains. And if I do this, I get a value now of 11,900. This value of 11,900 means that I can approximate. Now, what does this actually look like? When you set up for K, and by the way, write this down somewhere, like the back of your periodic table or something. Don't lose it because it is going to be a speed, a time saver. Now, what does this mean? So you've got this K expression like this. On the top, you have your two reactants, the two X's, and down here you've got 0.3 minus X. It's this minus X, this amount that is lost. This is what we can ignore if we can approximate. Just that X, that's the only one. But if we can, we are going to ignore that if we can approximate. And again, it's going to let us solve things with a greater speed. Now, here we go. We've got this reaction where phosgene is going to decompose into carbon monoxide and chlorine gas. The K on this reaction is 2.2 times 10 to the negative 10. And again, as soon as I see this really low K, I start thinking, can I approximate? I've got 1 mole in a 10-liter flask, so that means my initial concentration is going to be 0.1. So if I take 0.1 molarity and divide it by 2.2 times 10 to the negative 10 and get that value, and I think I did that. So we're going to be able to approximate. For some reason, I didn't write it down, but it's obvious that we can approximate on this thing. And that I think that would be 2.2 times 10 to the, well, don't worry about it. Okay, let's set up an ice chart on this reaction. The reaction is balanced, and our ice chart, initial change, and then equilibrium. We've got the phosgene, COCl2. We've got the carbon monoxide, and then the chlorine gas. The initial on this is the 0.10 molarity, and it's going to be a minus X situation. So the equilibrium, don't do that. The equilibrium story then here will be 0.10 minus X. These reactants, we're going to be starting at 0, so these are both going to be plus X's. So this will be concentration of X, and this will be concentration of X as well. So my K expression, K, will be equal to, on the top, the carbon monoxide, chlorine gas, and on the bottom, the COCl2, which is the phosgene. There's no coefficients here, so nothing is brought up to any sort of exponent. So we have k at 2.2 times 10 to the negative 10. And that will now be equal to, on the top here, x squared over this 0.10 minus x. And this is where we are going to approximate. So we're going to approximate this thing, and it's going to let us just work a little bit faster. So I'm going to take this value here, and I'm going to just ignore it like it doesn't exist. We're going to approximate it out. And that's because up here, 0.1 divided by 2.2 times 10 to the negative 10, which I didn't bother doing before, but I feel like I should, is, wow, well in the range of this thing. So it's greater than 1,000. 1, 2, 3, 4, 5, 6, 7, 8, 9. It's in the hundreds of millions, so we're good. All right. Now when we go to solve, what I now end up with is this. 2.2 times 10 to the negative 10 is equal to x squared over 0.1. So therefore 2.2 times 10 to the negative 11th is equal to x squared. And then I simply get my x value, which I brought in at 4.7, x equaling 4.7 times 10 to the negative 6. And that is the equilibrium concentration of this carbon monoxide. Because it's a single x, I don't have to add, subtract, or do anything to it. 4.7 times 10 to the negative 6, and that is its molarity. Square brackets for molarity. Okay, how we can approximate and how that works. I've given you your final practice on this, a little bit of approximation on one question, and again, a bonus question, something that's a little bit more challenging, something to take a look at, and that, so good luck with that. By the way, if you watch this video to the bitter end at this point, the word of the day is titration. Write that on your homework someplace and you will get extra bonus credit for it for watching the video to the end. Also, I've got to tell you, and that on this Friday, as we go into a weekend, I could not be more impressed with most of you, what you're doing and how you're coming along with this. It really, really, really leaves me just speechless at times. And that really, really pleased. Okay. Have a great weekend. Take care. Do whatever. Go outside. It's supposed to be really nice out. Bye-bye.